स्टूडेंट्स, ਅੱਜ ਦੀ ਕਲਾਸ ਵਿੱਚ ਤੁਹਾਡਾ ਸਵਾਗਤ ਹੈ। ਹਰ ਇੱਕ ਲਿਕੁਇਡ ਜੋ ਅਸੀਂ ਵੇਖਦੇ ਹਾਂ ਉਹ ਆਮ ਤੌਰ ਤੇ ਐਸਿਡ ਜਾਂ ਬੇਸ ਹੁੰਦਾ ਹੈ। ਐਸਿਡਸ ਅਤੇ ਬੇਸਿਸ ਸਾਡੇ ਆਲੇ ਦੁਆਲੇ ਹਰ ਥਾਂ ਤੇ ਮੌਜੂਦ ਹਨ, ਪਰ ਡਿਸਟਿਲਡ ਵਾਟਰ ਇਸ ਦੀ ਇੱਕ ਐਕਸੈਪਸ਼ਨ ਹੈ। ਐਸਿਡਸ ਸਾਡੇ ਸਰੀਰ ਵਿੱਚ ਵੀ ਛੋਟੇ-ਛੋਟੇ ਕੰਪਾਊਂਡਸ ਜਿਨ੍ਹਾਂ ਨੂੰ ਐਮੀਨੋ ਐਸਿਡਸ ਕਹਿੰਦੇ ਹਨ ਦੇ ਰੂਪ ਵਿੱਚ ਮੌਜੂਦ ਹਨ। ਕੁਝ ਫਲਾਂ ਵਿੱਚ ਸਾਈਟ੍ਰਿਕ ਐਸਿਡ ਹੁੰਦਾ ਹੈ। ਬੇਕਿੰਗ ਸੋਡਾ ਨੇਚਰ ਵਿੱਚ ਬੇਸਿਕ ਸੋਲਿਊਸ਼ਨ ਹੈ, ਜਦਕਿ ਸਿਰਕਾ ਇੱਕ ਐਸਿਡ ਹੈ। ਮੈਨੂੰ ਉਮੀਦ ਹੈ ਕਿ ਤੁਹਾਨੂੰ ਸਾਰਿਆਂ ਨੂੰ ਅੱਜ ਦੇ ਪਾਠ ਬਾਰੇ ਪਤਾ ਚੱਲ ਗਿਆ ਹੋਵੇਗਾ। ਇਹ ਹੈ ਐਸਿਡਸ ਐਂਡ ਬੇਸਿਸ। ਅੱਜ ਦੇ ਇਸ ਪਾਠ ਵਿੱਚ ਅਸੀਂ ਐਸਿਡਸ ਅਤੇ ਬੇਸਿਸ ਨਾਲ ਸੰਬੰਧਿਤ ਵੱਖ-ਵੱਖ ਥਿਊਰੀਜ਼ ਅਤੇ ਉਹਨਾਂ ਦੀਆਂ ਲਿਮਿਟੇਸ਼ਨਸ ਤੇ ਵਿਚਾਰ ਕਰਾਂਗੇ। ਇਸ ਤੋਂ ਇਲਾਵਾ ਅਸੀਂ ਆਪਣੇ ਆਲੇ ਦੁਆਲੇ ਮੌਜੂਦ ਵੱਖ-ਵੱਖ ਤਰ੍ਹਾਂ ਦੇ ਐਸਿਡਸ ਅਤੇ ਬੇਸਿਸ ਬਾਰੇ ਜਾਣ ਕੇ ਉਹਨਾਂ ਦੀਆਂ ਪ੍ਰੋਪਰਟੀਜ਼, ਉਹਨਾਂ ਦੇ ਕੈਮੀਕਲ ਰਿਐਕਸ਼ਨ ਬਾਰੇ ਵੀ ਚਰਚਾ ਕਰਾਂਗੇ।
Upon completion of this topic, learners will be able to discuss Arrhenius concept of acids and bases, discuss Bronsted-Lowry concept of acids and bases, discuss Lewis acid-base concept, give examples of acids and bases, recall the definition of pH scale, solve numerical problems.
We use some substances like vinegar, orange juice and lemon. Students, do you know what is common in all these foods? Absolutely correct. These all are sour in taste. These are named as acids as the word acid means sour. Students, do you know that acids have some specific properties? That is, acids liberate hydrogen with active metals like sodium, potassium, calcium, magnesium, etc. and also turns blue litmus red. Let us have a look at the table showing some sources, names of acids and formula of common acids.
First one is lemon. Which acid is present in it? Absolutely correct. It contains citric acid. The formula for citric acid is shown on the screen. Next example is apples. Do you know which acid is present in it? Yes, malic acid is present in apples. Formula of malic acid is shown on the screen. Let us take some more examples. Which acid is present in vinegar? Well done. It is acetic acid. What is the formula of acetic acid? Yes, it is CH3COOH. Which acid is present in soft drinks? Yes, it is carbonic acid. The formula of carbonic acid is H2CO3. Which acid is present in automobile batteries? Yes, it is sulfuric acid. Let us recall formula of sulfuric acid. Yes, it is H2SO4.
But there exists another class of compounds like bleach, soaps, toothpaste, and cleaning agents, window cleaners, and sodium hydrogen carbonate or bread soda, which are bitter to taste and are chemically opposite of acids. They have a soapy feel and turn red litmus blue. Let us take a few examples of a few common bases.
Let us see some sources of bases, their names and their formulae in the shown table. First one is oven cleaner. It contains sodium hydroxide. Let us recall formula of sodium hydroxide. Formula of sodium hydroxide is NaOH. Next is laxative, which contains magnesium hydroxide. Formula of magnesium hydroxide is MgOH whole twice. Another is drain cleaner, which contains potassium hydroxide. Formula of potassium hydroxide is KOH.
However, this classification is rather vague and there are many exceptions to it. Thus, many attempts were made to define acids and bases. The outcome of these attempts is three theories or concepts: Arrhenius concept of acids and bases, Bronsted-Lowry concept, and Lewis concept. Let us first take up Arrhenius concept of acids and bases. Arrhenius was a Swedish chemist. He had received a Nobel Prize in 1903 for his work on electrolytes. He had given a concept which is known as Arrhenius concept of acids and bases. This concept suggested definitions of acids and bases. When acids and bases dissolve in water, ions are formed. According to Arrhenius theory, an acid is a substance which produces hydrogen ions when dissolved in water, whereas a base is a substance which produces hydroxyl ions when dissolved in water. The role of water is very important in the acidity of a substance. This was prompted by the fact that gaseous hydrogen chloride is not acidic. But do you know what happens when it is dissolved in water? An acidic solution is produced. Let us discuss what happens on dissociation of water molecule.
Water molecules dissociate into hydrogen ions and hydroxide ions. We can also write it as shown here. Or water molecules dissociate to form hydronium ion and hydroxide ions. The special role of hydronium ion and the hydroxide ions in aqueous solutions becomes clear from this equilibrium. What is the difference between reaction 1 and reaction 2? In reaction 1, hydrogen ions are formed, but in reaction 2, hydronium ions are formed instead of hydrogen ions.
The reason is that hydrogen ion cannot exist alone in aqueous solution. Hydrogen ions combine with water molecules to form hydronium ions. For simplicity, chemists often use the notation H positive aqueous ion for the hydronium aqueous ion and call it the hydrogen ion. Please keep in mind that it is really the hydronium ion that exists in water and not the hydrogen ion. Students, we have discussed above Arrhenius concept of acids and bases. Now we will see dissociation of few compounds in water. Let us take an example of nitric acid.
Nitric acid, that is HNO3, reacts with water to form hydronium ions and nitrate ions. As you know, hydrogen ions given by HNO3 combines with water to form hydronium ion. Thus, HNO3 is an acid as per Arrhenius concept and is known as nitric acid.
Now we will see some more examples. What happens when these compounds are dissolved in water? Let us discuss. Let us take example of sodium hydroxide.
In water, sodium hydroxide dissociates to form sodium ions and hydroxide ions. Therefore, sodium hydroxide is a base as per Arrhenius concept.
Let us take another example. The compound is ammonium hydroxide.
In water, ammonium hydroxide dissociates to form ammonium ions and hydroxide ions. Therefore, ammonium hydroxide is a base as per Arrhenius concept.
Let us now discuss an interesting fact about acids and bases. What happens when we mix acids and bases? Acids and bases neutralize one another.
Because the hydrogen ion coming from an acid combines with the hydroxide ion coming from a base to form water as shown on the screen.
As we have completely understood the Arrhenius concept, let us discuss limitations of Arrhenius concept. It was found later that there are many reactions which do not take place in aqueous solutions. They take place in other solvents than water. Thus, Arrhenius concept was silent about the nature of such substances. This problem was addressed in 1923 by the Danish chemist Johannes Bronsted from 1879 to 1947 and the English chemist Thomas Lowry from 1874 to 1936 when they independently proposed a more general definition of acids and bases. And the study of acids and bases took a great step forward. This theory became as the Bronsted-Lowry theory of acids and bases. Bronsted-Lowry concept. According to this theory, an acid is a substance which has a tendency to give a proton. A base is a substance which has a tendency to accept a proton. In simple words, we can say that an acid is a proton donor while a base is a proton acceptor. This theory explains why pure acid behaves differently from its aqueous solutions. Since for an acid to behave as an H positive ion donor, it must have another substance present to accept the H positive ion. So, the water in the aqueous acid solution is behaving as a Bronsted-Lowry base and accepting an H positive ion. Generally, a base qualifying Bronsted-Lowry concept is termed as a Bronsted-Lowry base or simply Bronsted base, and an acid qualifying Bronsted-Lowry concept is termed as a Bronsted-Lowry acid or simply Bronsted acid. As we have discussed definition of acids and bases on the basis of Bronsted-Lowry concept, let us take examples of Bronsted acid and Bronsted bases. Examples of Bronsted bases are sulfate ions, phosphate ions. These take one or more hydrogen ions. They are proton acceptors. Hence, they all are Bronsted bases. We will study Bronsted acid and Bronsted bases together in chemical reactions. With the help of dissociation of some bases, let us try to understand this. First example is calcium oxide and water.
When calcium oxide is dissolved in water, it is converted to calcium hydroxide. Here the water molecule donates a proton and it acts as Bronsted acid. The calcium oxide accepts a proton and gives calcium hydroxide. Hence, it is a Bronsted base. Next example is hydrogen chloride and ammonia. Hydrogen chloride gas reacts with gaseous ammonia to form solid ammonium chloride. Hydrogen chloride is a proton donor and hence acts as a Bronsted acid, while ammonia is a proton acceptor and hence acts as a Bronsted base.
To sum up, we can say that according to Bronsted acid-base theory, all acid-base reactions involve the transfer of a hydrogen ion or a proton and are hence regarded as proton transfer reactions.
On the screen, we can see that water reacts with itself. For example, by transferring an H-positive ion from one molecule to another to form an H3O positive ion and an OH negative ion. Thus here, first H2O acts as Bronsted base and second H2O acts as Bronsted acid. Here again we can see that hydrochloric acid HCl reacts with water to form H3O positive ion and Cl negative ion. Thus, HCl donates a proton and hence acts as Bronsted acid, and H2O accepts a proton and thus acts as Bronsted base. In this chemical reaction, ammonia reacts with water to form NH4 positive ion and OH negative ion. Here, ammonia accepts a proton to form NH4 positive ion. Thus, NH3 acts as Bronsted base, but H2O donates a proton to form OH negative and thus acts as Bronsted acid.
If a substance behaves both as a Bronsted acid as well as a Bronsted base, then it is called amphoteric. Water has this ability. As well as reacting with acids, it can also react with Bronsted base. Students, now you have learned Bronsted-Lowry concept as well as Arrhenius concept. Can you tell why Bronsted-Lowry concept is superior to Arrhenius concept? Students, you will get answer to this if you tell me whether ammonia is an acid or a base. Yes, absolutely correct. It is a base. But we cannot explain nature of such type of bases with the help of Arrhenius concept, because Arrhenius base is a substance that releases hydroxide ion as a base. On the other hand, it is comparatively easier to understand with the help of Bronsted-Lowry concept, because Bronsted base is a substance that accepts the proton. Let us see an animation to understand this.
In the formation of ammonium chloride, gaseous ammonia can react with hydrogen chloride to give ammonium chloride. Here, ammonia is a recognized base as it can accept a proton to form ammonium ions. Hence, ammonia qualifies as a base according to Bronsted-Lowry concept.
Thus, release of hydroxide ion is not necessary to qualify as a base. Bronsted-Lowry concept. If we compare these two theories, we find that Arrhenius' concept of acids and bases is restricted to the study of substances which can release hydrogen ions and hydroxide ions in water. Thus, Arrhenius' concept of acids and bases is limited to aqueous solutions only. But Bronsted-Lowry concept is not limited to aqueous solutions. Moreover, it has a much wider scope. Another advantage of this concept is that it is not restricted to neutral molecules. Thus, acids and bases can be either neutral molecules or ions. Bronsted-Lowry concept further give rise to the concept of conjugate acid-base pairs. What are conjugate acid-base pairs? The acid and the conjugate base that are related to each other by donating and accepting a single proton are said to constitute a conjugate acid-base pair. To understand this definition, let us view an animation.
Consider a hypothetical acid-base reaction between the acid and the base. The acid gives up its proton and produces a new base. The new base that is related to the original acid is called a conjugate base. Similarly, the original base, after accepting a proton, gives a new acid, which is called a conjugate acid. Thus, in this equation, the two conjugate acid-base pairs are HA and A negative and HB and B negative.
It's time to discuss some more examples of conjugate acid-base pairs. Let us consider the reaction between hydrochloric acid, that is HCl in aqueous form, and ammonia.
Here hydrochloric acid and ammonia form the conjugate acid NH4 positive and the conjugate base Cl negative. Hydrochloric acid and chloride ion acts as conjugate acid-base pair. Also, ammonia and ammonium ion acts as conjugate acid-base pair. Now let us consider the reaction between acetic acid and water to form the conjugate base acetate ion and the conjugate acid hydronium ion. Acetic acid and acetate ion acts as conjugate pair. Water and hydronium ion acts as conjugate pair.
As we have completely understood Bronsted-Lowry concept, let us discuss limitations of Bronsted-Lowry concept. It is unable to explain the acidic behavior of certain substances like boron trifluoride, aluminum trichloride, etc. As these do not have any hydrogen and hence cannot donate a proton to behave as acid according to Bronsted-Lowry concept. Also, it cannot explain the reaction between acidic oxides like carbon dioxide, sulfur dioxide, sulfur trioxide, etc. and the basic oxides like calcium oxide, barium oxide, magnesium oxide, etc. which take place even in the absence of the solvent. Thus, in order to overcome these limitations, a new concept, Lewis concept, was put forward. What is Lewis concept? Students, let us have a look on the Lewis concept. In the early 1930s, G. N. Lewis proposed a more general model for acids and bases. According to Lewis theory, an acid is an electron pair acceptor. A base is an electron pair donor. Let us have a look on its examples. If the Lewis acid be denoted by A and Lewis base by B, then we can write a chemical equation in such a way.
Lewis base B is donating one electron pair to Lewis acid A and forming a complex AB.
The principal advantage of the Lewis theory is the way it expands the number of acids and therefore the number of acid-base reactions. Lewis acid. According to Lewis concept, molecules in which the central atom has incomplete octet, for example, boron trifluoride, aluminum trichloride, etc., can act as Lewis acid, or molecules in which the central atom has empty d orbitals, for example, silicon tetrafluoride, etc., can act as Lewis acid. Or molecules in which the atoms of dissimilar electronegativities are joined by multiple bonds. For example, carbon dioxide, sulfur dioxide, etc., can act as Lewis acid. Also, simple cations can act as Lewis acids, for example, sodium ion, potassium ion, calcium ion, etc. Now, let us discuss Lewis bases. According to Lewis concept, neutral species with at least one lone pair of electrons can act as Lewis bases. For example, ammonia, etc., can act as Lewis base. Also, anions such as cyanide, hydroxide, etc., can act as Lewis base. Let us now quickly recall what is pH scale. Acidity is measured by using pH scale. In 1909, Sorensen introduced a term pH for expressing the concentration of hydrogen ions of a dilute solution. Let us try to define pH scale.
pH of a solution is defined as the magnitude of the negative power to which 10 must be raised in order to express the hydrogen ion concentration. It is written as pH is equal to minus log value of hydrogen ion concentration. Here, H positive is the concentration of hydrogen ions in moles per liter. Let us try to solve a numerical problem based on pH. Numerical 1. The hydrogen ion concentration of a fruit juice is 3.3 multiplied by 10 raised to the power minus 2 molar. What is the pH of the juice? Is it acidic or
basic?
And the solution is? We are aware of the definition of pH. It is defined as the negative logarithm of the concentration of hydrogen ion. It is written as given hydrogen ion concentration is equal to 3.3 into 10 raised to the power minus 2. Substituting this value of hydrogen ion concentration into the definitions of pH, we get pH is equal to minus log value of 3.3 into 10 raised to the power minus 2. Putting log value, we find pH value equal to 1.48. Since the pH is less than 7, the solution is acidic.
Students, ਮੈਨੂੰ ਉਮੀਦ ਹੈ ਕਿ ਤੁਸੀਂ ਅੱਜ ਦੇ ਲੈਸਨ ਨੂੰ ਚੰਗੀ ਤਰ੍ਹਾਂ ਸਮਝ ਲਿਆ ਹੋਵੇਗਾ। ਧਿਆਨ ਦੇਣ ਲਈ ਬਹੁਤ-ਬਹੁਤ ਧੰਨਵਾਦ। ਅਗਲੀ ਕਲਾਸ ਵਿੱਚ ਫਿਰ ਮਿਲਾਂਗੇ।